recording it since you might need to go back through these instructions again. So you're going to go into Pearson, go to the Multimedia Library, go to Chapter 15, to Section 15.3. And the only thing I want you to check, so that it won't take long to find it, because there's a lot of different stuff, is check the interactive figure. That's the only thing. Just check that. And tell it to find it. And it'll bring it up at the bottom of the page. Okay? And all you have to do is click on it. We're going to do this way rather than you have to sit and calculate areas of rectangles 122 times to do just 2 or 3 problems, because it's tedious. It's like a lot of the stuff we did in the beginning in Chapter 11. It's very tedious arithmetic to have to do. Even if you had to do it on the calculator, it's very tedious. This gives you the idea without your having to do all that arithmetic. So what we're going to do, and you can open it up full screen if you want to, but you do want to view it large, which means that you may not really want to open it full screen. You may want to resize your screen yourself. But there's a slider bar on the side of it. So the function that we're looking at here is the function 2x plus 5. And that's a linear function. And because we have formulas in geometry for finding the area of a trapezoid, and that's what this is. It's the area of it. It's a trapezoid. It has a slanted side. We could actually find the actual area. So the actual area of that trapezoid is 36 units. Right now, I'm not showing you how I got that approximate area, but I'm going to have it show you how I found the approximate area by having it show you, and I'm not going to do 4 rectangles. I'm going to start with just 2. So if I do what are called left-hand rectangles, that means that the rectangle that's on the left starts basically at the middle of this, since I've got 2 rectangles. And the problem with using these 2 rectangles here to approximate the area under that line is that the area of the rectangles is too small. The actual area is more than the area of the rectangles. Now, I could try to counteract that by making what are called right-hand rectangles, which means that I use the rightmost edge to determine the height of the right-hand rectangle. But the problem with those rectangles is they overestimate the area by a lot. Okay? The midpoint actually turns out to be the best estimate because it splits the difference. Midpoint rectangles always do the best job because it leaves some of the overage, which is canceled out by some of the underestimation. And even on all of these, I don't care if I make 2 rectangles or 4 rectangles or 10 rectangles or 20 rectangles. It doesn't matter how many rectangles I make, because this is a straight line figure, the rectangles, if I use midpoint rectangles, give me the exact area that I'm looking for. And that's what we're going to be talking about in 15.4 and 15.5, the area between a function and the x-axis. Now, doing it here is kind of foolish because, like we said, we can use a geometry formula to find the exact area, but we know that most of the functions that we run into are not straight lines. They're mostly curves. So we're going to go back, and I'm going to go back to my handout. And instead of looking at that, we're going to look at the function negative x squared plus 4, and we're going to look at the area that starts at 0 and goes to 2. And I'm going to show you how we actually do that. So what we do is we go up here and we pick, instead of 2x plus 5, we pick the second function down. Now, this is not something I want to get into with you right now, because part of the area is above and part of it's below. We will talk about that later on in the hour, but I don't want to talk about it right now. I want us to start and not go all the way to 4. I want us just to go to 2, because that cuts off just this little chunk right here. Okay? So we're going to go from A equals 0 to A equals 2, and we're going to start out with only 2 rectangles. And notice here, with only 2 rectangles, that the actual area of the rectangles is close, but it's not as close as maybe what we would like it to be. But if we double the number of rectangles and instead make 4 rectangles, notice that the area starts getting closer. And if you made 8 rectangles instead of 4, then it gets to be a better approximation still. Because what's happening is we make more and more rectangles as there's less and less error. And if we doubled 8 and went to 16 rectangles, then the area is really, really close. It's only off by about 3/10,000. And if we go all the way to 20 rectangles, then we're only off by a couple of 10,000. Now, the idea here is, could I make more than 20 rectangles if I wanted to? Yeah. I could make 100 if I wanted to. The only problem is, every time I increase the number of times, the number of rectangles I put under there, that means that's that many more arithmetic problems I have to do. But calculus lets us avoid the arithmetic. If you can think back to what we talked about in Chapter 11, sometimes we let x approach infinity. How about if you could put as many rectangles as you wanted to and not have to do the arithmetic? Well, that's what integration does. That's what a definite integral is. It actually says find the area under this curve between the curve and the x-axis, but let the number of rectangles that you use approach infinity, which means the integral is going to give you the exact area from point A to point B underneath that curve that's cut off by the x-axis. So what I want you to do is, after you've explored this function, there's some specific questions that I ask you about that one. And then there's some specific questions about that one. And then there's some specific questions about this one. And it's all going to involve you changing the beginning and the ending of the area to the numbers that I tell you for A and B. And then change the number of rectangles. You're going to go from having 2 rectangles to having 4 to having 8 to having 16, or maybe go from 3 to 6 to 9 to 12 and so forth. But the questions on the handout are very specific, and it's just to encourage you to look at that app and see that what happens is that this area here, when you do 4 rectangles, it's close. If you do 8, it's closer. If you do 20, it's really close. And then I ask you, what do you think would happen if you could use 10,000 rectangles? Because the most that app lets you use is 20. So what do you think would happen if you don't? Do you see a pattern going on here? Because that's going to be the basis of what we're going to be looking at tonight in Section 15.4. So we'll close that down, and we will start talking about Section 15.4. Yes, Mr. PowerPoint, come up. There we go. Which is called, scarily enough, the fundamental theorem of calculus, which sounds all ominous and formal and everything. But it basically just says what I just told you. It says that if you're trying to approximate the area under a curve, you can take the antiderivative and use that with some numerical substitution, some arithmetic, and find the exact area under the curve using that antiderivative. So what we've already learned about is how to do antiderivatives, and hopefully you've had a little bit of practice with that by now. So this is what the fundamental theorem says, and one of my students in my earlier class said, and rightly so, she said, that just looks like a bunch of gibberish to me. And I understand. It does. So what we're going to have to do is we're going to have to try to put this in English. The only thing I'm going to point out to you is that this symbol, capital F of X, with a line after it, B and A, basically is used to represent the difference in the antiderivative evaluated at B minus the antiderivative evaluated at A. Basically, you take your antiderivative, you plug in the upper value, then you plug in the lower value. You subtract the two, and you're done. And all of that's arithmetic, and you can do all of it on your calculator. So this is our first example. We're going to find the integral of 4t to the third power, and then find the integral from 2 to 1 using that antiderivative. Okay? So I'm going to ask you first, since you're the ones who need to practice this, find me the integral of 4t to the third dt. Use your power rule. So what is the integral of 4t to the third? What is the antiderivative? Okay. You bring your 3 underneath and add 1, and then add 4 to the power. Add 1 to the power. So what you wind up with is 4t to the fourth over 4, which comes out to be just t to the fourth. Okay? There's your first step. First step. Now, no, I did not put the constant. Okay? I did not put the constant because you don't really have to do the constant if you're doing a definite integral, because all the constant does is it raises and lowers the function and then the limits of the area that you want that function under. So it doesn't really change anything in the long run. So we don't have to have the constant if we've got what are called the limits of integration. And the limits of integration are these two numbers, 1 and 2. Those are called your limits of integration. Okay? And what that means that we're going to do is we're first going to find the value of this antiderivative, t to the fourth. First, we're going to use the 2 in place of t, which makes 2 to the fourth. Then we're going to use the 1 in place of the t. And then we're going to subtract the 2 of them. Just use arithmetic. So 2 to the fourth power is 16. 1 to the fourth power is 1. And that means then that the value of our integral is equal to 15, which is 16 minus 1. Okay? Now, the arithmetic isn't difficult. Sometimes it will be a little more difficult than what this is, but it really shouldn't be difficult. You do have a way that you can evaluate these using your calculator and be sure that you're right. Now, there's actually two ways to do it, but the way that I'm going to show you is actually to draw a graph and evaluate that integral. Okay? So what I'm going to do is we're going to go to the y equals menu, and I'm going to clear everything off. I'm going to go up here and put the original integral in, which is 4t to the third dt. Only I have to use x. So it's going to be 4x to the third. Okay, you put the function in that you're integrating. And since we're going from 1 to 2, I'm going to go over here and set my window up to go from 0 to 3, just so that I can see it. Okay? And I'm going to, let's go about -2 below the x-axis. Well, no, let's just let the calculator find a good window. So from 0 to 3, counting by ones, we're going to go zoom and go to the zoom 0, which zooms and fits a window to the function, so we don't have to hunt for it. It's going to find it for us. And it found a pretty good window. Okay? The only adjustment I'm going to make is because I know it's going to print across the bottom of the screen, is I'm going to have it go, since that goes up as high as 108, I'm going to have it go down to about -20, so that I've got some space down here when I actually use my calculate menu, I can see what it's saying. So once you've got a good graph, we're trying to find the value of the area under the curve from 1, which is right along there, to 2, which is right along here. Okay, let me see. Okay, see that? That's what the problem is. Oh, no, it's fine. There you go. Anytime you get that error invalid dim, that's always what it is. It's got a stat flaw. Okay, so now that we've got a graph of it, this is how you actually find the area, and you're going to get a picture of the area under the curve that you're looking for. So you go to second, trace, which is your calculate menu, and we've used that a lot in this class and in 1530 to find intersections and all kinds of things. But we're going to go down now to number 7. Number 7 is the integral of a function, f of x dx. And this one only works on the graphing screen. It doesn't work anywhere else. If you use this one, you can't use it and copy it over to the home screen and do anything. There's another one that does that, but this you'd rather do it this way. So the integral f of x dx, choose enter, and it goes and it says, what is your lower limit? What's the lower limit of your integration? Well, it's 1. So you type a 1 and hit enter. And then it says, okay, what is the upper limit? Well, the upper limit is 2. So you tell it the upper limit is 2 and hit enter. And it does the rest. Okay? It actually shows you the area between the curve and the x-axis and tells you exactly what it is. Okay? So there's no reason to get these wrong because you bungled up the arithmetic. I do that all the time. I did it big time earlier this afternoon. I messed up the arithmetic putting a sign in wrong. And we almost never found it, but we knew the answer was what it was supposed to be because the calculator told us what it was supposed to be. And then we finally found the error in the arithmetic. what the DT shows you is what is in, it's like a sign. The DT is like a sign that's pointing to the what we call the integrand, and says that's a derivative. See, I'm DT. That means that's a derivative. That's really once you do that, if you don't have limits of integration so that you can do the math, then you just put a plus C after it. Okay? No. All you're going to use is you actually take your integral. You take your integral first, which is that, and then it reduces and simplifies to that. And normally we would say that's t to the fourth plus c, that constant of integration that raises or lowers it for the family of functions. But since we're going to put two numbers in, we don't need that constant. It actually gets canceled out in the process. So when we do this, then we just do the integral by going, okay, here's the antiderivative, evaluated at 2, evaluated at 1, and then subtract. And the key to remember is it's always top minus bottom. If you do it backwards, you'll get a negative answer, and that'll tell you that that's what you've done because area is not negative. Okay? So basically this is an application, an extension of your lesson on how you use the power rule. And that's what the fundamental theorem does, is it lets you figure out the area between a curve and the x-axis. And since you haven't seen an application of that yet, you're sitting there saying, well, that's nice, but so what? But there is an application to it that we're going to get to at the end of this section. And then everything in section 15.4 is applications. So I'm going to skip over quite a bit of this because it just explains why you don't need the constant. And this tries to explain to you what 15.3 was telling you. That's why we did 15.3 instead of doing this, because I think watching that little figure, watching those little rectangles go closer and closer to being actually underneath that curve, all of them, is actually what this is getting at. And this basically says the variable doesn't matter. If you've got a chain rule function, it still works. Now, the only one of these I want to talk about, because we talked about these two in the previous, that basically if you've got a constant times the function, the constant comes out front. If you've got several terms, break it up and evaluate each term. But this one here is stating something so obvious, I've always wondered why they include it as one of the properties. Because all this says is if you are integrating a function from 1 to 1, well, 1's here and 1's here, and there's no area between 1 and 1 because you can't find the area of a line. That area is 0. A line doesn't have area. It has length, but no width. Okay, so that one's just a statement that, you know, if your limits match, all you did was draw a line. You don't get an area for that. This is going to be important in the next section because it says that if you're integrating from A to B and something funky happens between A and B, like maybe part of the area is above the x-axis and part of it's below the x-axis, you can still add the two areas together. What you need to do is you need to break it up and go from A to wherever that craziness occurs, and then start there again and integrate from there, that's point C, to the end of the interval. So that one will make more sense to you in a problem we're going to do toward the end of the section. This one just says that if you swap your limits and do it backwards, you know, A is supposed to be smaller than B, but if A is smaller than B and you put B and A in opposite positions, all that happens is it puts a negative sign in front of your area. Okay? So this is actually what that third one is saying. This one doesn't do anything that says that anything happened at C, but it tells you basically if you wanted to, you could find the integral from A to C and add it to the integral from C to B, and you get the integral all the way from A to B. And I'll remind you of this when we come to the one where it's going to make a difference that we need to break it up and do it that way. So here's our next example. And your job, like it was a minute ago, is to find for me the integral. Find the antiderivative. And I'm just setting this up for us for a few minutes. So remember, your first step is just to do the antiderivative. And remember, we won't really need that constant, but normally when you're doing it, you would have the constant if you didn't have the limits. So that's 3, that's 3, that's 2, that's 2, 1, and that's 1. So my antiderivative is 3 goes into 6 2 times, x to the third, minus 2 goes into 3. Well, it doesn't, so we're going to leave it like it is. Plus 5x. First step is done. Second step is the arithmetic. So we're going to evaluate it, that expression, plugging in x equals 2, and then plugging in x equals 5. There we go. Yeah, because there's a blind missing on the window. And I don't see anything I can prop up there. Maybe I do. Well, almost. There. So we need to do 2 sets of arithmetic there. And I learned my lesson the hard way earlier today. I'm not going to do it in my head, especially not this time of day. So I'm going to use the calculator. So 2 times 5 to the third power minus 3/2, get over there, times 5 squared plus 5 times 5 is 237.5. And then I will redo that calculation and change the 5 to a 2. Second enter. And it just saves a lot of typing time when you're trying to do it up here especially. And that is 20. So what that means then is that's going to be 217.5, which is the answer to the question.
Why
237.5 minus 20, because you're subtracting. I don't do it straight across the page the way that the textbook does it, because I think it's easier for you to see and easier to follow if I separate the two steps. No, just circle the answer and put it up there where it goes. You know, however you want to do your own scratch work is up to you. Now, because we want to check it, I have put the equation, the integrand, into y1. Okay? And y1 is turned on so that it will graph. This will only work if you put your equation that you're integrating in y1 or some y value. It has to be in a y value, and it has to be turned on so that it'll graph. Because it only operates on the ones that it can see on the graphing screen. So then we're going to go, and I set my window up since our limits were 2 and 5. I set my window up to go from 0 to 6. And then I'm going to go zoom and 0. And let it do its thing. And it found me a pretty good window, but what I want is I want to move that up off the bottom a little bit. So I'm just going to go back to the window, and it's only going from 4 to over 203. Well, I'll be happy if it goes down to about negative 25. That way I can see a little bit underneath the graph. And then you go second, trace to the calculate menu and down to number 7. And the lower limit was 2, and the upper limit was 5. And it shades in the area for you, and then it tells you how much it was. Okay? So there's all the arithmetic. That's the way that the textbook works it out, because this is the example out of the textbook. But I tried to break it down to where it made more sense the way that I had been teaching you how to do it. But they come up with 435 over 2, which is 217.5. Now this is the one where we're going to have to do substitution. So again, the first step, do the antiderivative. So this integral, I can't do things with radicals, but I sure can change that into a 1/2 power. And over here is x dx. And this is, as I said, a u substitution because I've got a function raised to a power. I moved it from here over to here. Okay? So if this is u, we're undoing a chain rule. We're going backwards on a chain rule. We talked about that last time. So if that's u, then I need du. And du is the derivative of 25 minus x squared. So what's the derivative of 25 minus x squared? And then, of course, that is a derivative, so it's a dx. Do I have what I need? I have part of it, but I don't have the negative 2. So like we said last time, I can put in the negative 2 if I put in negative 1/2 in the front, because negative 1/2 times negative 2 is equal to positive 1. So by introducing both of those factors, I've actually only introduced a 1 into the problem. You have to have the negative 2 before you can actually do the derivative. Once you put it in, it's going to disappear along with x dx, but the negative 1/2 is going to hang around because it's a multiplier now. So that means now that my integral, using my u substitution, is going to be negative 1/2 times u to the 1/2 plus 1 over 1/2 plus 1. And, of course, we know that 1/2 plus 1 is 3/2. And in order to avoid having all those fractions, I'm going to rewrite this way. I'm going to pull my 1/2 out in front, times u to the 3/2. And rather than divide by 3/2, I'm going to multiply by 2/3 because that's how you divide by a fraction, is you flip the fraction over and you multiply with it. That's what drives this. Division by this is the same as multiplying by its reciprocal. That's why you had to learn all that stuff a long time ago. So now, doing fraction arithmetic, 2 times 1 times 3 is 6. 1 times 2 is 2. U to the 3/2. And I've still got that negative sign, so I need to keep that negative sign out front. And normally I would have plus c on the end of it, but because this is a definite integral, what I have instead is the limits from 0 to 5. And it's not absolutely a requirement that you do this, but you probably will want to. 2 cancels into 6 and leaves that being a 1 and makes that a 3. So this is the same as the integral with simpler arithmetic of negative u to the 3/2 divided by 3 and evaluated at those same limits. But I've still got that u in there. So now I need to go put u back in. This is the value of u right here. Yeah, it's still negative. So are we good so far? Okay, let's put in the 5 first. So there's the first one. And the second one's going to be that. And remember that we're subtracting the second one. So what's going to happen is those signs are going to cancel out. This is actually going to become an addition problem. So once again, we're going to use the calculator. Make sure we don't mess up any arithmetic, because I've already done enough of that for a lifetime today. So negative parentheses 25 minus 5 squared raised to the power 3 divided by 2, and then divided by 3, I'm still going to get 0. So that whole first thing is 0. So then we just got to figure out what the other one is. That's going to be negative 125 divided by 3. And as a fraction, because the book's actually going to do it as a fraction, although there's nothing wrong with the decimal, is negative 125 over 3. And since we're subtracting that, just like I already mentioned to you over here, that's actually going to turn out to be positive. And if we're talking about money rather than keeping fractions, we would go to a decimal and call that 41.67. And once again, we can evaluate that integral with the calculator and make sure that we're getting it right. So the original integral was x times the square root of 25 minus x squared. And the window needs to cover at least 0 to 5. So negative 1 to 6 should be plenty. So there it goes. And I do the integral starting at 0 and going to 5. And there's our area. Okay? Think you can handle these? Because you can use this in this section and the next one. You can do the numerical integration on your calculator. So if it was an application problem, after you've set it up, if you don't want to go through all the calculus, since you've got a numerical value to put into it, then you can go ahead and plug in your values and tell me that's what you did and tell me the answer. Okay? If we've got technology, we should use it. So that's all of their work, and it comes out to be the same as our work. And then we get exactly the same thing that they got, 125 over 3. Now, this is just one little caution so that you don't think this is a magic bullet. The numerical integration always works. There are some little tricks to doing the numerical integration that you always need to look at a graph before you actually do it. So don't ever go straight to numerical integration. Always look at the graph before you do the numerical integration. There are some problems, like this one here in particular, that you cannot take an antiderivative. The only way to do it is with numerical integration. But the ones that you're going to have to do for this for all your homework, well, there will be an antiderivative. You can't always take the ones of the problems I give you. This is just that you be aware that in some places, like in prob and stats, that there's going to be integrals that they can't do except numerically. The other thing we need to keep in mind is that f of x has to be positive on the interval, because if it goes below the x-axis, that makes the area, as far as the calculator is concerned, negative, because it doesn't understand that area isn't negative. It doesn't understand that it's actually a physical property and therefore can't be positive or negative. So that's one of the places where, as I mentioned earlier, if you reverse your limits, it's trying to go backwards and it thinks that made it negative. But if you look at this problem, x squared minus 4 from 0 to 2, well, from 0 to 2, the area there is below the x-axis. And if you ask the calculator to give you the answer, it's going to tell you it's 16/3. And I'm not going to go through the actual calculus. We're going to do it on the calculator so that you'll see it. So this function is x squared minus 4. And we're needing to go on from, let's say, about -1 to 4. And we could look around for the window, but since we already know this is going to go negative, then I'm going to set it up that way. So I'm going to let it go down to about -4. And start at about +2. So you see there that your graph, when you're going from 1 to 3, is going to be negative. How did I have that scale? Okay, that does make sense. So then when we do the integration, the lower limit here is going to be 1, and the upper limit's going to be 3, because they told us that's what it was. I'm sorry, 2, not 3, 2. So it actually fills in and it gives you a negative area. I must have done something wrong, because that's not 16/3 is not 1 2/3. Oh, they graphed x squared minus 3x. That's the book's bad, not ours. Let's try this so that it'll at least match the graph. Oh, it is 0. They have botched the whole thing. They don't even have the right problem. Okay. It's not actually either one. Okay, let me go back and try this again. Let's do the one we started out with, which was x squared minus 4, and the limits are 0 to 2. And that is the right answer. That is the right answer. So you must be right. I put in the wrong limit the second time. But notice that it's saying that area is negative. Okay? It's up to us to know that that area is not really negative, because area can't be negative. So the caution here is that when you get an answer that's negative, you need to realize you need to drop the negative sign and take the absolute value. Okay? That's not going to be as important here as it is going to be in another problem we're going to do here in a minute. Okay, and this is example 5. That I must have copied that graph over there, and it doesn't belong there. Let me delete it out of there. No, I don't want to add any text. Stop that. So that's our next problem, is to do f of x equals x squared minus 3x. So there's the graph of x squared minus 3x. And if we do the integration, starting at, it looks like this is going from 1 to 3. It tells us the area is negative 3 1/3, when in fact it's actually 3 1/3. So just be aware that the calculator looks at area below the x-axis, between the curve and the x-axis. When the curve is below the x-axis, it thinks that's negative, because numerically it is. And that's not really a problem here, because we know it's not, and we can just drop the negative sign. Is everybody getting these right now? Now, we did that one on the calculator. You can do the calculus, and it comes out to be the same thing. You do your antiderivative and evaluate it the way we have been, and it comes out to be negative 10/3. So the only real point here is that this one comes out to be negative, so you have to take the absolute value of the answer. This is the reason you needed to pay attention to that, because this happens realistically in business quite a bit. If we're trying to find the area on the graph of x squared minus 4 from 0 to 4, we're going to have a problem. Because here's what the calculator tells us it is. So remember, our lower limit is 0 and our upper limit's 4. I may have to adjust the graph for you to be able to see all of it. Yeah, I will. I need to raise it up. Let's see, it goes up to about, let's say, 15. So there's the whole area. Okay? That's not the right answer. Right. The calculator has arrived at that answer by calculating this area, which it assumed was all negative, and this area, which it assumed was positive, and it added them together, and it's come up with an answer that's too small. Okay? Now, we can get the calculator to tell us the right answer, but we have to break this up. So what has to happen is we have to recognize that the break, or remember I said that you may have to break it into two areas and find this area plus this area because the graph does something funky. Well, it did something funky. It has an x-intercept so that part of your area is below the x-axis and part of it's above the x-axis. And we can see, even on the graphing calculator, this suggests that you set that equal to 0 and solve for x. Well, yeah, you can do that. Whoops. And what it turns out is you get 2 and negative 2, but if you've already graphed it, you pretty much know that's 2. And if you don't know that's 2, you use your root function and find out that it's 2. So what you want to do is you want to break your integral up and go from 0 to 2, and then go from 2 to 4. And since the area that is from 0 to 2 is negative, then you take away the negative sign. But there's no way to get the calculator to tell you the right answer unless you break it up and do it step by step. So be careful that you look at the graph before you accept that number answer the calculator gives you. If you see an area under the x-axis as well as above it, then the answer the calculator gives you with numerical integration is not correct. You need to go back and check your work. So what we would have to do is what it shows us to do here. Integrate x squared minus 4 from 0 to 2. And since the integral of x squared minus 4 is 1/3 times x cubed minus 4x, then we would evaluate that at 0 and at 2, and that comes out to be 8/3 minus 8, which is a negative number, so we change it to a positive number. And then add that to the same integral, 1/3 x cubed minus 4x, but plug in 4, and plug in 2, and do that subtraction. The reason you only see one subtraction here is that if you put in x equals 0, that whole thing becomes 0. So you're subtracting 0 from it. So if I can help make that a little bit more clear. Because I know a lot of people are like my student from the earlier classes, that just looks like gibberish. Oh, I don't have that one. That's not nice. Let's see if I've got it further down the stack. Nope, sure don't. I'll just copy it over. Okay, so because we realized by looking at the graph that this is what happened, we got some area here and here, and that this place where that changed from being below to above was at x equals 2. We break the integral up and go from 0 to 2, x squared minus 4 dx, plus the integral from 2 to 4 of the same function, x squared minus 4 dx. And when we do the calculus part of it, this comes out to be, let's just do this one over here so we can just use it twice. This is u. So du is equal to 2x. I'm sorry, not 2x. No, yeah, it is 2x. My brain hasn't completely fried. It just thinks it has. So I don't have the 2. So I need to put the 2 here, and then I'll put a 1/2 outside. So that means on both of these, I'm going to do that. So then when I do the integration, that's going to be 1/2 times u, which is x squared minus 4. And that's going to become squared, because there's a power of 1 here, and then we're going to divide by 2. So if I separate that back out, 1/2 times x squared minus 4 quantity squared, over 2, that actually becomes x squared minus 4 squared divided by 4. And I think that matches with what they did. What did they get? 3. Oh, 2 plus 1 is 3. Sorry. They didn't do a u substitution. Never mind. Because they didn't have to. My bad. So this is going to be x to the third divided by 3 minus 4x. And it's going to be evaluated from 0 to 2. And this is the one where we're going to take the absolute value. And then we're going to subtract the same integral, x to the third over 3 minus 4x. And it's going to be evaluated at 2 and at 4. So for this one, just to distinguish it, that's going to be 2 cubed over 3 minus 4 times 2 minus 0 cubed over 3 minus 4 times 0. And that's going to give us 8 over 3 minus 8 minus 0 minus 0 is 0. And then this one gives us 4 cubed over 3 minus 4 times 4 minus 2 cubed over 3 minus 4 times 2. And this turns out to be the same as that. So when we do this one, this is 4 cubed is 64 over 3 minus 16 minus 8/3 minus 8. And we're going to add these two together, but we have to take the absolute value of this one because this comes out to be negative. That's negative 16/3, which means it's going to be positive 16/3 after I take the absolute value. And then this is also 16/3. And that's positive 16/3. And since we're subtracting 16/3 minus 16/3, and again, that's, let's see, that was negative because of this. That's actually the value of this. So we're subtracting a negative. That's going to turn out to be altogether 16/3 from the upper limit, or the first part, added to 16/3 minus times minus is plus 16/3. Which is 48 over 3, if I did all the arithmetic right, which turns out to be positive 16. Okay? And that is what they got. So even though the calculator initially told us the area was, what, 5 2/3? It's actually 16. That's the total area. And that's what this is cautioning you about, is that if you do the entire integral all at one fell swoop, that's what's going to happen. It'll even happen to you if you're just doing the regular integration. If you don't break it up, you're going to miss part of your area. And the more important thing to remember, too, is if it is really an example that is an application problem, for example, let's suppose that function we just looked at represents the annual rate of profit for a company, where their profit's increasing and decreasing. Then 16/3 represents the total profit for the company over the whole 4-year period. Okay? The 5.66666, the 5 2/3 that the original calculator came up with, is the total profit. Because realistically, the integral between 0 and 2, because that was below your x-axis, that was when your profit was negative. That was when you were losing money. So that's actually a loss for the first 2 years. And then the integral from 2 to 4 is 32 over 3, which means they were actually making money. So their overall profit is 32/3 minus 16/3, which is 16/3, although the total of the shaded area is 16. So when you're thinking about an applications problem, you may have to think about it differently. Area under the curve represents a negative whatever it's going on in the problem. Negative cost, negative not demand or supply, but maybe negative profit or something like that, especially in profit. In profit, that's going to be a very challenging thing to remember. So here's a quick summary, and then we're going to do the application problem, and then we'll take a break and do the next section. First step, always, always, always sketch a graph. Don't ever not do a graph. Because if you don't do the graph, you're going to miss something important that might cost you. If there's any x-intercepts on the function, on the interval you're looking at, be sure and find out what they are. And that breaks it up into subregions, so that's where you're going to have to do two separate integrals. And the definite integral is positive when it's below the x-axis and negative, positive above the x-axis and negative below. So if you're actually only looking for area, use absolute values. And then the total area is the sum of all the areas of the individual regions. So this is the problem we talked about last week when we first started this chapter. The yearly rate of consumption of natural gas in trillions of cubic feet for a certain city is C prime of T, which tells you that that's the consumption per year, is what that's actually giving you, since T is in years, is C prime of T equals T plus e to the 0.01 T. T equals 0 corresponds to 2,000. What they want to know is what's the total amount of natural gas that city used in the 10 years from 2005 to 2015. Our goal is to be able to answer that. So what's going on here is we're going to integrate from 5 to 15 because we're interested in the total consumption over that 10-year period. And this is the derivative, so we want the actual consumption, the total consumption function. So the integral of T is T squared over 2. And the integral of e to the 0.01t is e to the 0.01t divided by the derivative of its exponent, which is 0.01. So we're going to plug in 15 squared over 2 plus e to the 0.01 times 15, and the answer should come out to be 112.5. And then we're going to plug in 5 squared over 2 plus e to the 0.01 times 5 divided by 0.01. And that comes out to be 12.5, and both of those come out to be 100 times e to the 0.15 for the first one and 0.05 for the last one. Because dividing by 0.01 is the same as multiplying by 100. So that's where that 100 came from. It comes from dividing by the 0.01. And it comes out to be about 111 trillion cubic feet of natural gas. And this one would, again, be one that's easy to verify on your calculator. You go to your function, x plus e to the power of 0.01 x. We have to use x's instead of t's. And we need to graph it. We could actually graph it from 0 to about 20. Starting in 2000 and going to 2020. And let the calculator find a window to get us started. And notice that it looks almost linear. It is curved, but on the window we're looking at, it looks almost linear. So I'm going to change the x-min to about -5 and the max up to about 25. So there's our function. And we want to find the integral starting at year 5, which is 2005, and going to year 15, which is 2015. And it's 111.05631. Okay? I kind of expect you to use your calculator a lot with these last two sections. Unless I specifically tell you I want to see all the integral parts, feel free to use your calculator on definite integrals. Just be sure you draw that graph first. So that finishes section 15.4. Does anybody have any questions, any thoughts before we take a break? Let you get some oxygen going in your brain, your veins and brains again. Okay, let's take, let's give you about 15 minutes. It'll give you time to walk around. If you need to walk upstairs and get a snack or something, you can do that.